Hello, pirates. Today, we're going to discuss balancing chemical equations. Back in our thermodynamics unit, we discussed the law of conservation of energy, which stated that energy cannot be created or destroyed. It can only be converted from one form to another. In the next two units, we're going to be using the law of conservation of matter, which similarly states that matter cannot be created or destroyed. Before we continue, let's take a look at the anatomy of a chemical equation. On the left, we have the reactants. These are the chemicals that are going to react with one another, hence the name reactants. On the right side, we have the products, or the chemicals that are produced as a result of the reactants. In the middle, we have a yield sign separating them. The yield sign is similar to the equal sign in mathematics, except the two quantities aren't equal to one another. In this case, it's more of a before and after scenario. You'll also notice that there are subscript letters with parentheses around them. This describes the states that the reactants or the products are in. We have the traditional states of matter, so S stands for solid, the L stands for liquid, and the G stands for gas. But there are also two others. In the product side, you'll often see a PPT, or precipitate. This is a newly formed solid. And you'll also see AQ. AQ stands for aqueous solution, or something that's been dissolved in water. You'll also notice in front of the chemical formulas, you might see numbers with a line under them. These are the coefficients. This tells you how many parts there are. So in this particular example, there's 1 part H2SO4, 2 parts NaOH, and they produce 1 part Na2SO4 and 2 parts of H2O or water. We also have the concept of diatomic molecules. We also touched on this a bit in the ionic bonding unit, but it comes up a lot now, so it's worth reiterating. There are 7 diatomic molecules. We have H2, O2, N2, Cl2, Br2, I2, and F2. And then we also have 2 polyatomic ions, phosphorus, which exists in groups of 4, and sulfur, which exists in clusters of 8. And remember, diatomic and polyatomic molecules only exist when the molecules are by themselves or in their elemental states. Once they form to make compounds, then the diatomic and polyatomic rules no longer apply. Now that we have the background done, let's take a look at some of the rules for balancing equations. One of the best ways to do this is to make an inventory of the number of atoms or molecules you have on both the reactant side and the product side of an equation. Remember, the only changes that you can make are the coefficients. You can't change the numbers in the formulas. If you do that, you no longer have the same compounds, and then you would have a different equation altogether. And once you make a change to a coefficient, it's important to remember to reflect that in your inventory count. And now for some rules of thumb, some more informal things to help you balance equations. So whenever possible, keep polyatomic ions together. It makes the balancing a lot easier. If you have oxygens or hydrogen atoms that are by themselves, i.e. they're not part of a polyatomic ion, be sure to balance the oxygens last and the hydrogens second to last. They tend to work themselves out that way. Remember, it's okay to unbalance something in your inventory. You can always rebalance it in another step. And lastly, if you find yourself going back and forth, and it seems like an endless loop while balancing an equation, it's okay to erase everything and start the process all over again. So let's take a look at a chemical equation. Let's take the combination of hydrogen and oxygen to yield water. So when we write that out, we have hydrogen gas plus oxygen gas yield H2O, and water at room temperature is a liquid. But remember, both hydrogen and oxygen are diatomic, so they exist in groups of 2. All right, so now that we have that, when you write a chemical equation, it's helpful to write little lines in front of each of the reactants and products. That way you have a place to add your coefficients. So now let's create our inventory. When I do this, I like to put it under the yield sign. That way everything on the left is a reactant and everything on the right is a product. So in this, we have hydrogen and oxygen. So now let's take a count. On the left side, on the reactant side, we have 2 hydrogens, so I would write a 2. On the right side, we also have 2 hydrogens, so you write a 2 on that side. On the left side, we have 2 oxygens, and on the right side, we only have 1. So when we take a look, we notice we have 2 hydrogens on the left and 2 on the right, so those are balanced. We also have 2 oxygens on the left, but only 1 on the right. Now we need to make sure that we have equal numbers on both sides. We can't have an oxygen that just simply disappeared. So in order to change that, we'll put a 2 as the coefficient to the H2O. So 2 is my coefficient times the 1 oxygen in the water molecule means I now have 2 oxygens there. However, when I put a number in the coefficient, I've doubled everything in that molecule. So not only did I double the number of oxygens, but I've also doubled the number of hydrogens. So 2 hydrogens in a water times 2 means I now have 4 hydrogens. I've actually unbalanced the hydrogens, but that's all right. We can actually go back and rebalance the hydrogens on the left. So what I can do is I can make the coefficient in front of the H2 on the left side a 2. So 2 times 2 gives me 4. So I have 4 hydrogens on the left, 4 on the right, 2 oxygens on the left, 2 on the right. So my coefficients are 2, 1, and 2. Now, just like before, in chemistry, we tend not to write ones. So you can write it like this, or if you really like, you could put a 1 there, but it's not required. Let's take a look at another example. Here we have iron being reacted with oxygen, and it yields Fe2O3, or rust. So once again, we need to write out all the atoms involved in the reaction under the yield sign. So we have iron and we have oxygen. And then we need to take an inventory. We have 1 iron on the left and we have 2 on the right. We have 2 oxygens on the left and we have 3 on the right. So let's start balancing. At the top, we have 1 iron on the left, 2 on the right. So we need to change the coefficient. We need to make it where we have 2 irons. So 2 is the coefficient times 1 iron, means we have to redo our inventory and say we have 2 irons. So now the irons are balanced. But we have the oxygen. We have 2 on the left and 3 on the right. When you come across a situation like this, it's not as simple as having 1 and 2 where you simply multiply it. There's nothing you can multiply 2 by to get to 3. At least that's a whole number. So what we do is we find the lowest common multiple. What's the smallest number that both 2 and 3 multiply out to? And of course, that answer is 6. So on the left, I have 2 oxygens and I need to get to 6. What coefficient could I use, or what can I multiply 2 by to get to 6? And that answer is 3. 3 times 2 gives me 6. So on the right, I have 3 oxygens and I need to get to 6. What can I multiply 3 by to get to 6? And the answer is 2. So I put a 2 as a coefficient. 2 times 3 gives me 6. However, when I multiply the oxygen by 2, I also need to do the same thing for the iron because the coefficient applies to both. So 2 is a coefficient times the 2 iron gives me 4. So once again, I've unbalanced the irons. So now what I need to do is I need to go back and change the coefficient for iron. There is 4 on the right. There also needs to be 4 on the left. So I'm going to change the coefficient from 2 to 4. And once I do that, I'm going to change my inventory because there are now 4 irons. And now everything's balanced. We have 4 irons on the left and 4 on the right. We have 6 oxygens on the left and 6 on the right. Let's take a look at an example with a polyatomic. Here we have Fe2 parenthesis SO4 parenthesis 3 plus KOH, and that yields Fe parenthesis OH3 and K2SO4. So here we have the polyatomic SO4. What we need to do is we need to make sure that this still exists as a polyatomic on the product side. And if we look, we still have SO4. Believe it or not, there's actually a second polyatomic in here. If you remember back to the ionic bonding unit, OH is also polyatomic. And if you look on the product side, OH actually stays together as well. So when we go ahead and write all our atoms and molecules under the yield sign, we can leave SO4 and OH together. Now you could do these separately, but leaving them together makes this process go much quicker. Now that we have the atoms and molecules under the yield sign, let's take our inventory. We have 2 irons on the left and 1 on the right. We have 3 sulfate groups on the left and 1 on the right. We have 1 potassium on the left and 2 on the right, and 1 hydroxide on the left and 3 on the right. Now, it really doesn't matter where you start. It'll eventually work out the same, but let's just start at the top. So we have 2 irons on the left and only 1 on the right. So we need to change the coefficient on the right to a 2. So 2 is a coefficient times 1 iron means I now have 2 irons. We've now balanced the irons. However, when I put a 2 as a coefficient in front of the iron 3 hydroxide, not only did I multiply the iron by 2, but I also multiplied the hydroxide by 2. So I started with 3 hydroxide, and I multiplied it by 2, so 3 times 2 gives me 6. I need to reflect this in my inventory. So now it gets doubled. I've unbalanced the hydroxide, or unbalanced it further, so let's look at that one. I have 6 hydroxide on the right and only 1 on the left. So what times 1 gives us 6? It would be 6. So I'll write a 6 as a coefficient in front of the KOH. So 6 times 1 gives us 6 for the hydroxide. But once again, when I multiply the hydroxide by 6, I also have to multiply the potassium by 6. So again, 6 times 1 gives us 6. Now, let's continue with the potassium. I have 6 on the left and only 2 on the right. What can I multiply 2 by to get to 6? And that answer is 3. So on the right side, in front of K2SO4, I'm going to put a 3, because 3 times the 2 potassium gives us 6. And again, when I multiply the potassium by 3, I also need to multiply the SO4 by 3. And once you know it, by changing the inventory to 3, I've now matched the sulfate. So if we go back and look, I have 2 irons on the left, 2 on the right, 3 sulfates on the left, 3 on the right, 6 potassiums on the left, 6 on the right, 6 hydroxides on the left, and 6 on the right. So our coefficients are 1, 6, 2, and 3. Let's take a look at one more reaction. Our final reaction is a special type of reaction that we'll learn about later called a combustion. So what we have here is a hydrocarbon, and this is propane, and it's burned in oxygen, and it gives us carbon dioxide and water. So just like any others, we need to write the molecules under the yield sign. In this case, it's CHNO. So let's count how many atoms we have on the reactant and product sides. We have 3 carbons on the left and 1 on the right. We have 8 hydrogens on the left and 2 on the right. We have 2 oxygens on the left, but if we look on the right, there are oxygens in both of the molecules. So we have to add them up. There are 2 oxygens in the carbon dioxide and 1 in the H2O or water molecule. So 2 plus 1 gives us 3. So as we remember from our rule of thumbs, we like to do oxygens last and hydrogens second to last, which means we need to start with the carbons. So we have 3 carbons on the left and 1 on the right. So we need to change our coefficient to a 3. So 3 times 1 gives us 3 carbons. But not only do I triple the number of carbons, I also triple the number of oxygens. So 3 times 2 gives us 6 oxygens, plus the 1 in the water means we now have 7 oxygens. The carbons are good. Now let's balance the hydrogens. I have 8 hydrogens on the left and 2 on the right. What can I multiply 2 by to get to 8? I need to multiply by 4. So I use 4 as the coefficient. So 4 times 2 gives us 8 hydrogens. But remember, not only did I multiply the hydrogens by 4, I did the same thing to the oxygens. So 4 times 1 gives me 4, plus the 6 from the carbon dioxide gives me 10. Now I have 10 oxygens on the right and 2 on the left. What can I multiply 2 by to get to 10? I multiply by 5. So 5 times 2 gives me 10 oxygens. So I have 3 carbons on each side, 8 hydrogens on each side, and 10 oxygens on each side. So there are a lot more different types of balancing equations, but here's a little sampling. Again, this is one of the things where the more you practice it, the easier they're going to get. That's all for today. Have a great day and go Pirates.